Hello everybody, my name is Chris, and today we're going to talk about transfer learning. I think transfer learning is really cool because it lets you take a small data set and actually create a really accurate model. We're going to do this by leveraging very large networks that were trained for many hours or even days on much larger data sets than ours, and actually transfer that knowledge into our own network made specifically for our classification problem. So today we're going to be working with the Freiburg grocery dataset, which is a small dataset, about 4,000 images of various grocery products. And we want to train our classifier to tell us what type of grocery products those are. So let's take a look at the data. So first we're going to import our Keras model layers so we can build a Keras model. And we're also importing ResNet 50, which is a image classification network actually out of Microsoft Research that's very large, and we're going to be able to transfer knowledge from it into our own network. So first we need to load our training data. So here we're splitting our training data into a train and a test, as well as extracting the class names from this utility library called groceries. And let's take a look at one of those images actually looks like. There you go, a jar of pickles. Hopefully, we can train our machine to tell us that. So let's look at what the other classes in the data set look like. We got beans, cake, pasta, and my favorite, vinegar. All right, let's see how the data is actually distributed. So as you can see, some of the classes don't have nearly as many examples as others. Hopefully, transfer learning can help to compensate for this. So before we can train our model, we need to convert our categories, which are going to be numbers between 0 and 25, into one hot encoded vectors. So we're calling toCategorical on our labels. And now, just to see how we can perform on this data set with a very simple perceptron, let's go ahead, normalize our data, and then just create a single layer perceptron model. We're going to use categorical cross entropy for our loss because this is a multi-class classification problem. Our good old friend, the atom optimizer. And we also want to view accuracy so we can have a better metric to comprehend what's going on. Lastly, we're calling wb.init so we can visualize our metrics. And let's go ahead and train this model. Okay, so looks like we aren't doing so well. Our validation accuracy is 0.04%. This is very troubling. Our accuracy on the training data is even lower. I mean, I look at this and I feel ill. There has to be a better way. So Keras makes it really easy to leverage the research community's progress in computer vision models. So here, we're going to import ResNet 50 and actually download the pre-trained weights from training on ImageNet, which is an image data set with millions of images that takes many days to train. So with this one line, we're pulling in cutting-edge computer vision research. Let's go ahead and take a look at a model summary to see what this network looks like. Oh man, so many layers. ResNet 50 is much more complicated than our simple perceptron. You can see things like batch normalization, many different convolutions, and then even this funny add layer. So what ResNet does is it actually branches off and takes features from earlier in the network and adds them back in later layers. And this helps the network train better and allows researchers to make an even deeper network, which gives it more expressibility and accuracy. I can just keep on scrolling. So to see what this network can actually do, let's run it on a picture of an elephant, because why not? So here we're loading in our elephant. We're changing its size to 224 pixels by 224 pixels because the network expects that size. Then we're expanding the dimensions because we need to include our batch dimension. And we call this really important function preprocess input. So when they trained ResNet, the researchers used a very specific way of preprocessing the images. And we're going to use their exact same logic to do that on our own data so that we can have high accuracy results coming out of the model. Lastly, we just call predict, and we're using this nice helper method, decode predictions, which are going to change the various indices into the last layer and tell us exactly what category that it's predicting. And look at that. The network output a tusker with 49% accuracy, an Indian elephant with 34% accuracy, and there's a slight chance we're looking at an African elephant. Now, I personally probably wouldn't be able to tell you the difference between these three kinds of elephants, but a network this powerful is actually able to do it with a high degree of accuracy. But we don't want this network to tell us the categories that it had trained on. We want it to tell us our categories for our grocery data set. So let's look at a way that we can actually do that. First, let's take our grocery data set and preprocess it exactly the same way that the ResNet authors did. Now, we can actually go into the ResNet model and pull out specific layers that we want to use. In this case, we're going to pull out the second to last layer, which is called the average pool layer. And now we can create a new model with the same input to our ResNet model, but now instead of outputting 1,000 categories, we're going to output this last layer as our final category. So let's take a look and see what this model actually looks like. It's still a massive model, but now instead of 1,000 categories at the bottom, we have a 2048 linked vector, which are going to contain what we hope to be the most important features from our data set. So now we can actually take our preprocessed grocery data set and run it through this new model that we've created and actually extract the features. So now we're going to transform our images into 2048 linked vectors of numbers that we can use to train a new model on. And we hope that ResNet has created features that are going to be much easier to learn from than our original image data. We're going to do the same for our test data. And then finally, we can create a new model, which is a simple perceptron again, with 25 categories for our data set, using the same loss and optimizer as we did earlier. Let's go ahead and fit it and see if we can get better accuracy than our first try. Look at that. Right off the bat, we're getting into 80% validation accuracy. You might also notice that we have a bit of an overfitting problem, but there are actually additional techniques we can use to ensure that the network generalizes well across our data set, and we can fix this issue. So instead of just extracting the features, which is great because it actually makes our model train really fast, a disadvantage is now if we actually deploy this model, we're going to have to deploy two models side by side and always put our input imagery through all of ResNet and then separately pass that output into the next model. Keras makes it really easy for us to make a single model where the output of the ResNet model can just go directly into our perceptron. So we do this here by creating a new model. We add our ResNet layers and our new final dense layer. Then we turn all of our layers to be trainable equals false in the ResNet network. So when we're training this network, we don't want any of the layers to train in ResNet. Instead, we're just going to tune the weights in our final dense layer. So now you can see there are 23 million parameters in this network, but only 51,000 of them are trainable. Now if we run training, you'll see that it actually takes a lot longer to train. This is because every batch, we're passing that data all the way through the ResNet network and doing all of those convolutions and different arithmetic. So it's taking much longer as opposed to using the cached output features that we had used before. But the advantage of this is now you have a single model that you can use to continue to retrain as your data set maybe grows or you change different labels in your data set, as well as it's much easier to deploy your models. But you see we're getting essentially the same accuracy as we were getting by just extracting the features and then training this last layer. All right, so there's one more technique we can use with transfer learning that'll actually give us even more accuracy. This is known as fine-tuning. So instead of just training our layers that we added at the end of the network, we can actually take a subset of the layers in the ResNet network and allow them to train as well. So the reason behind this is the way these networks tend to learn is that the layers much higher up tend to extract much more higher level features, things that would be shared common amongst all the classes in your data set, whereas the layers lower in the network tend to be much more specific and are looking at shapes and different edges that are going to be very specific to your classes, or in this case, the classes that ResNet was trained on. So we can actually take these final layers and fine-tune them, enable them to change their weights so that they're better suited for our classes, while still enabling the very generic layers at the top of the network to pass down the most meaningful information for our new classifier. So to do this, we actually set the ResNet to be trainable now, and we go into that network and actually, in this case, just say the final 11 layers out of the 100 or so that are in ResNet, we're going to allow to train, whereas the first layers are all not going to be trainable. So one thing to note when you're fine-tuning is that because the weights have been trained on a very large data set and are going to be very specific to the ResNet data set, when we start to fine-tune those weights and move them, we're likely going to want to do that much more slowly than we would in a normal network. So this is a case where instead of just setting optimizer equal to Atom, you would want to actually instantiate a new instance of the optimizer and slow down the learning rate. So we really want to move those weights in the last layers a little by little, and this can really prevent overfitting on our data set, which can be easy given it's so small and we have so many parameters. And look at that. With only a few lines, we were able to leverage cutting-edge models to actually get 72% accuracy on our Freiburg grocery data set. Remember, we started at less than 1% accuracy. I'd say that's a pretty good day at the office.